most basic one is gradient descent. Okay, they just simply use a learning rate and the direction of partial differentiation so that we can find the optimized weight. And we introduce momentum. Every time you do the partial differentiation, if you have momentum, okay, you can increase the speed of finding the optimized weight. I would like to show you another one, another concept. It's called ADA. ADA stands for adaptation. It is an algorithm for gradient descent-based optimization that does just this. It adapts the learning rate to parameters, perform smaller updates, which means low learning rate for parameters associated with frequently occurring features, blah, 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 blah. Most important thing is that performing smaller update, that is low learning rate. What does that mean? You can see that there are a lot of different optimizers. Its prefix is ADA. So basically, for example, ADA delta, Adam, ADA max, those optimizers, they adapt the concept of learning rate adaptation. So let's take a look. Maybe we can use this figure again, okay? Again, how do we adapt learning rate? Which means low. Sometimes, okay, when we do such kind of search, we can simply call it search. From this point to this point to this point to this point. At the end, maybe it's right here. We stop right here. However, if we decide to do one more iteration to find the lowest one, maybe after that, okay, it's right here. Maybe the next one is, the direction is right here, so it comes to here. And you figure out, it seems like the MS value increase. So theta prime, theta minus theta, delta J theta, something like that, right? So here's the learning rate. So at the end of your iteration, usually we can find such kind of situation. When you approach the lowest MSE value, maybe you don't need to have such a big learning rate. Maybe when you approach the lower MSE value, you should decrease your learning rate so that you can do a very delicate move from previous weight to the next weight. That is called ADA. ADA. I think it is quite easy to understand. When you approach the lowest MSE value, the more close you are, you should decrease your learning rate. You can approach this closely. So basically, all those following optimizers, they adapt such kind of concept so that you can find the lowest MS value. Of course, there are some other variations. There are too many optimizers, mathematical details. Okay, the only thing you need to know is this concept. Okay, so if possible, okay, go home and take a look at those. Oh, there are some very interesting figure. So if possible, try to take a look at this article. If you do not follow all those mathematical things, that's okay as long as you know what concept we use. So here's a comparison. The surface is the loss function. The star is the lowest loss function value. So we randomly start from different place. Optimizer, SGD, momentum, blah, 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 blah. Okay, so you can see that how quick or how slow or how they change their direction to the optimized point. Go home and take a look. You can see that SGD is always the slowest one because it is the basic one. It's always the slowest one, the red data point. So the green one is the momentum, right? So the momentum will faster. You can see the green line is faster, but the learning rate might be too large. So the green one might go to some higher place, some hill， 就是中文有没有？红色的就是 SGD，SGD 永远都是最慢，因为它没有修正过。那你看绿色那个 momentum， 因为它有动量的关系，所以你就想开车一样嘛，它会比较冲出去一点。那因为 momentum 会冲出去嘛，所以它有时候会反而没有到比较低的点，它会跑到山坡上面去，然后再倒车，就像绿色的现在这个样子，然后才会往对的方向去。所以 momentum 如果一开始冲太快的话，其实不是好事。你看绿色要到后期，它后期就很棒，对，后期就顺着这是等高线的哈，就到低谷里面去，好吗？ 那你看那个 AD 开头的，我们就看蓝色的 AD 杠好了。AD 杠一开始方向不对嘛，好，那没关系，反正 AD 杠因为它会渐渐，你注意看那个蓝色的那个点，它一开始比较快，但它越来越慢，越来越慢，有没有看到？现在蓝色越来越慢，有没有看到？那就是我们刚刚讲的嘛，我们会调整 learning rate 让它变得比较小，那比较小之后啊，你就看那个蓝色会越来越 approach 那个星星。如果它这个真的有做完的，就是这个图如果继续跑的话，你会发现那个蓝色的点会真的更靠近星星的中心点，然后红色的点不见得会靠近星星的中心点，因为 SGD 没有调整 learning rate， 所以它会在山谷的低地中间这样跳来跳去，它到不了低地，因为它的 learning rate 没有变小。可是蓝色的 AD 杠，因为它的 learning rate 会越来越小，越来越小，越来越小，所以它就可以越往下，越往下，越往下。啊，它的 granularity 比较细一点。啊，这个是直观上的说法了。所以你自己在做这个 neural network 的时候，要想一想哪一种比较适合你的 application。可是通常我们想不出来，因为比如说随便给你一个问题，你就做了一个 neural network， 然后你就 apply 下去的时候，哪一个好不知道怎么办？用试的，就真的 practical 上就是很愚蠢的，只能用试的，好吗？好，我用英文再讲一遍咯。Okay, take a look at this figure. Okay, we have several different optimizers. For example, SGD. SGD is always the slowest one because it does not adaptively change its learning rate. So it is always the slowest one. Okay, for the momentum, okay, the green one. The momentum always has the faster because it has momentum. But if the momentum is not correct, the direction of momentum is not direct, we can see that the green line initially it goes to the wrong place because it moved too fast. The momentum is too fast, so it goes up to the hill and then come back to the basin. That is the green one. And we can see the eta guard, which is the blue one. We can see that the blue dot they move faster at the first place, although it toward to the wrong direction. But however, you can see that the blue dot decrease its speed gradually. Do you see that? Slow down, slow down. You can see the blue point slow down. The green momentum still goes fast at the end. But at the end, the blue point decrease its speed. That is because we decrease the learning rate so that we only take a very small step for each iteration. Theoretically, if we compare the red SGD and the blue ADA guard, usually ADA guard can approach the lower loss function value because it decreases its learning rate. So it has a fine granularity to go to lowest point. But SGD does not change its learning rate, so it may not approach to the lowest value. It will jump between two. So we can draw a figure like this. That is MSE, like this. For SGD, it goes to this direction, right? This direction. Because SGD does not change its learning rate, so maybe it jumps between these two points and cannot approach the lowest point. But however, the ADA, it has a larger learning rate and smaller one, smaller one, smaller one, smaller one, smaller one, smaller one. So it may goes to the lowest point. Okay, that's the difference between them. So make sure you understand several concepts. One is SGD. You update your weight gradually and determine it by the direction and the learning rate. Second, momentum. Okay, you can keep the direction you have. Third, you use ADA to decrease your learning rate at the end of your learning. So make sure you understand those things. So let's go back to here. So we have talked about sequence stack model. Okay, how do you build your model? You have to build this kind of this model by your own. You should take some time to take a look at this specific video. Okay, so take a look at this video and follow those codes. Okay, the video will explain those codes. Okay, so maybe I can select one of the example. In this case, we have part 1. We have a regression problem which is called Boston housing price prediction with feed-forward neural network. You already know what is neural network, right? But what is feed-forward? That means all the information passed from the left-hand side to the right hand side. That's called feed forward. So if you write codes, it may like this. Okay, we have keywords. So we have data. We have training data, training labels, which means Y. Testing features, testing data, and testing labels. Okay. So next one is to build a model. So the model is quite simple. Sequential state, right? It is a very simple model. So it simply just use dense layer. Okay. It has 20 nodes. The activation function is TensorFlow's ReLU. So input shape is, it depends on how many features you input. So next layer is simply just a dense layer, only has one node. The output of this node simply just do the prediction. The prediction of housing price. The output layer has only one node, which output the prediction value of the house in poster. After you construct your model, then you compile your model. So you have to select several different things, including what kind of optimizer you want to use. And here, use Adam. It is a variation of adaptive learning rate. So the learning rate will decrease at the end of the iteration. The loss function is MSE because it's a regression problem. So we use MSE. So matrix means after that, I would like to show the MSE value and MAE value. So that is the model. However, I have one thing that I need to inform you is that sometimes those examples are created when TensorFlow is in its version 1. But currently, TensorFlow version is version 2. So sometimes the code may have compatibility problem. So make sure the example you download or the example you reference has correct version. In practical, okay, I strongly recommend you only use TensorFlow v2 to write your code, to compile your code, to learn how to write TensorFlow code. We just simply drop version 1, okay, because it will take some time. So after you use this model, okay, this is quite simple. The next one is line number 7 is to build a model. Okay, so we have the model. Number 10, model.fit. The fit function means please use all the training data, which is training features, training labels, to train the model. So they will do the partial differentiation to find all the weight defined in your models. Okay, so A part right here is that I would like to run 1000 iterations to do the partial differentiation. Okay, so that's 1000. We will talk about validation data next time, okay, not this time. And then you simply just output the value, okay, there's 0 different ways. Take a look at this example. So it's quite simple. Load the data, make the table. Okay, you have features, you have labels, training data, testing data. You make your own model by using sequential. Okay, you can design different layers, different nodes, different activation function, optimizers, learning rate, and simply just call model.fit, and that's done. And we can output all those weight. Okay, we can test the things. Okay, just take a look at this one. Again, we can see that we only see the blue line. Since we have 1000 epoch, right? So that is the first 600 epoch. We can see that for each iteration, for each time we do partial differentiation, the mean square error is the y-axis decrease because we are approaching to the lowest value of MSE. So by changing the weight every time, we go more close to the lowest MSE. So take a look at this blue line, which is the training error, which is the MSE value for each iteration. So I think that is good enough. Okay, so next time we will talk about how to use another layer called convolution, and we use another example which is quite popular, handwrite digital, and we would like to classify, okay, different numbers. Take a look at this video. Okay, it's your homework.